Hello, everyone. I'm going to solve a problem that I've seen once in Holiday Resnick, but I've actually found two different ways to solve it. One you can solve with conservation of momentum, and another you can solve by realizing that the center of mass of the system has to stay perfectly still. In this first video, I'm going to solve the problem by conserving momentum, and it's going to be sort of like a train car like they did in the original Holiday Resnick problem, but in this case I'm just making it a really big box because I want the sizes to be so large that they're really unreasonable to be a train car. But you can just imagine a big heavy box on wheels that has very little friction, and it's going to have a cannon inside of it and a cannonball, and we're going to fire the cannonball from one end of the box. It's going to hit the other end of the box and stick to the wall so it stays right there. At the end of all that, we're going to see how much the whole system has moved to the left, say, and I'm going to solve that now with conservation of momentum. So let me turn on my document cam. So what we're looking at is a big box. This big box is going to be roughly 100 meters long. It's going to have a mass that's equal to 3,800 kilograms. At the 1 meter mark, in other words, 1 meter from this end, we'll have a cannon set up. And the cannonball will be there as well. The mass of the cannon will be equal to 200 kilograms. I'm assuming everything's at least three sig figs here. And the mass of the actual cannonball, which I'll say lower MB, is going to be 40 kilograms. So you see that that's basically 1/100th of the total mass of this whole system. Okay. I'm going to embed this in an XY coordinate system. I'm going to say the origin is right below this corner. So this is the Y axis and this is the X axis. And I'll assume the box is fairly symmetrical so that we can say assume the center of mass of the system is actually at the 50 meter mark. And that should do pretty well. Let me try to get this a little better focus. I don't like it too much. Sometimes it does better if I got a word up in here from a marker. There you go. That looks pretty good to me. All right. So what we're going to do is we're going to assume that the cannonball is actually fired at a velocity relative to Earth equal to 200 meters per second. So I'll call that velocity of the ball relative to Earth. What I know is that initially the momentum, Pi, is equal to the mass of the ball times the velocity of the ball initially, plus the mass of the cannon times the velocity of the cannon initially, plus the mass of the box times the velocity of the big box initially. I realize now I used a bad subscript because the B occurs twice. So I'll use a lowercase b from now on. But in each of these cases right now, that velocity 0, that velocity 0, that velocity 0. So the total momentum before the actual cannon being fired is equal to 0. So after the cannon is fired, I'm going to call this P2. Then we have the mass of the ball. So again, I'm changing this to a lowercase b to keep from confusing it with the mass of the box. I had the mass of the ball times the velocity of the ball with respect to Earth. I'll again make that a lowercase b as well. I also have the mass of the cannon, which is stuck to the box, plus the mass of the box. They should have a common velocity u. And since momentum is conserved, I should say that 0 is equal to the mass of the ball, which is 40 kilograms. Again, I'm assuming 3 sig figs there, times 200 meters per second, plus, notice 3,800 plus 200 is 4,800, or 4,000, excuse me, 4,000 kilograms times the velocity of the box. You can see that since all that adds up to 0, you're going to get the velocity of the box is equal to negative, basically it's the little mass mb over the total mass of the cart and the box, or excuse me, of the cannon and the box, times the velocity of the ball with respect to Earth, which I've already put in these numbers. Of course, 40 times 200 is 8,000 kilograms meters per second. And that, of course, will be divided by 4,000 kilograms. And that gives us, of course, negative 2.00 meters per second. That's the velocity of the train, or excuse me, the box with respect to Earth. So I'll put a subscript E on it just to remind us that. Here's the reason why. Because now that this has been fired, conservation of momentum says that there's going to be a recoil of the box and cannon system. The box and cannon system is going to start to pull off this way. And the cannonball, of course, is going to move this way. The cannonball moving at 200 meters per second with respect to the Earth, and the actual box moving at 2 meters per second with respect to the Earth. I need to figure out what the velocity of the ball relative to the train car is, because it's going to go not necessarily a distance of 99, even though it started at 1 meter and the end is 100 meters. Even though the end is 100 meters, it's not going to go 99 because the train, the ball is going to be moving at 200 meters per second. But at the same time, the actual train car is going to be moving at 2 meters per second. So it actually has a relative velocity. So the velocity of the ball with respect to the train car, or with respect to the box, I should say, should be equal to the velocity of the box with respect to the Earth plus the velocity of the Earth with respect to the box. Well, we don't know what the velocity of the Earth with respect to the box is, but we do know what the velocity of the box with respect to the Earth is. That's lowercase b. It's actually negative 2 meters per second. So if I want to flip these indices, I just change the sign to a negative using the typical formula for addition of velocities. Then I'll get that's equal to VBE minus V big BE. So VBE, the velocity of the ball with respect to Earth, is 200 meters per second, minus now the velocity of the box with respect to Earth is negative 2.00 meters per second. And I think you can see that's going to give me 202 meters per second for the velocity of the ball with respect to the box. Now the distance that's going to travel is going to be close to 99, but not exactly 99 meters. What we know, well, it will be 99 meters with respect to the box. So as long as we use the velocity of the ball with respect to the box, we'll be good to go. So the time allowed for the box to go that distance is in fact equal to t, which is distance divided by velocity. Well, the distance within the box system is 100 meters minus 1 meter, which I tend to call, just say d, right? Saying this distance right here is d. And divided by the velocity, which would be 202 meters per second. I think you can see now that that should actually give you 490 milliseconds. So that's how much time this ball is flying. Why do we want to know that? Well, we know that as long as the ball is flying, the train car is recoiling this way at 2 meters per second. And then when it hits the other side, conservation of momentum is going to dictate that all three will be moving at the exact same speed. And that exact same speed must be given by m for the ball plus m for the cannon plus m for the box times one common speed equals the initial momentum, which was in fact 0. And since that initial momentum is 0, that's when the train car will stop moving and we will be able to tell how far the train has actually moved. Or excuse me, the box has actually moved. So in this case, we're going to say that the distance traveled, x, is actually equal to the velocity of the box with respect to Earth times the time we just calculated. So that'd be 200, or excuse me, 2.00 meters per second for the velocity of the box with respect to Earth times the 490 times 10 to the negative third seconds. And that gives me, and remember this was actually a negative, so it actually gives me an x position or an x movement of the box equal to negative 980 times 10 to the negative third meters. So what we just discovered is that the train car, according to conservation of momentum, the train car will move a distance x such that this end and this end and the center of mass and the cannon, everything will move a distance x, and that x is actually equal to 980 millimeters, which is obviously not very far at all. So basically the train car will have moved meters, 980 times 10 to the negative third meters in that time allotted, and it'll move to the left. So that's the ultimate effect. The ball will now be in the far right hand edge of the train car, embedded in the wall at the 100-meter mark within the train coordinate system. But now the whole train, cannonball, and cannon will have been shifted over by position X. So in the next part, the next video I make, I'm going to actually show you how to do this exact same problem, only we're going to solve it using the fact that it's a closed system so that the center of mass won't move because the net force acting on it externally is zero. All the forces going on in here are totally internal forces. So if we're actually able to do it, then we should get that this thing moved 980 millimeters to the left. So that ends that.